I'm going to talk a little bit about, after quite a few efforts, managed to get some funding. So I'm going to talk about a little bit of the project that was recently funded called MultiXscale. Well, it's not officially funded yet. We're still in the negotiation stage for the grant agreement, but it will come. So just to give you some key points about it, what it is first. It's part of the Euro HPC ecosystem, I guess you could call it. So it's falls underneath that funding scheme. So it's an HPC center of excellence underneath that scheme, of which there are something like 10, 11, I believe, something like that now. So there's highly scalable centers of excellence, which are like their specific focus is on the extreme scale side of things. And then we fall under the other kind of center of excellence, which more also includes like high throughput computing and things like that. So not necessarily using the entire machine at these exascale machines at any single time. So it gives us some more flexibility there. It's a 4-year project. The start date, it looks like it's going to be February of next year, but that's still not 100% decided, but you could probably safely say that it'll be Q1 of next year. The budget in total is just under 6 million euros. So the way Euro HPC works is that 50% of that money comes from the EU, and the other 50% is already has been agreed to be given by the national funding. And of the 6 million euros, about roughly 50% of that money is going to EC related activities, right? So this is essentially, it's a collaboration between two organizations, I guess you could say. So EC and also a network called CCAM. So CCAM is a 50-year-old network of scientists that are active in general, just in simulation. So it actually stands for Centre, my French is not good, Centre Européen de Calcul Atomique et Moléculaire, so atomic and molecular physics. But they're around a long time, and their scope has kind of gradually extended, right? And the network of scientists there is probably about like 2,500 scientists. So the total number of partners is 16 partners. Yeah, you can imagine how it's split, right? So basically EC primarily is doing like technical related activities, and then the CCAM network is the one that's providing all the scientific project. And the HPC centers of excellence in general are thematic, right? Or they focus on a particular area of science. So like you have things like climate and weather related things, and you have things like astrophysics, but they cover like domains. So our domain is multi-scale physics. So it's multi-scale simulations, and we have within the project we'll cover 3 key use cases. So one of those is helicopter design and the certification for civil transport, and the other one is battery applications. The idea being to support the sustainable energy transition, and the last one is biomedical. So that's ultrasound, to use that for diagnostics and biomedical applications. So our objectives, we had this nice, took us a while to get this cut from a graphic like this that kind of tries to outline those and how they work together. But basically we want to design applications for multi-scale modeling, looking towards the exascale and how we might implement workflows or whatever on exascale type systems. And we want to provision those, we want to support those, and we have to maintain those for the community, right? That's key software packages. We want to accelerate the application development, looking at the exascale. So we want to kind of insert concepts or inject ideas that will help people to move towards exascale, scientists to move towards exascale in the short, medium, and even long term. So we want to port the software to the different systems that will be available within Euro HPC. We want to obviously verify that software works. We want to distribute it among the community. So not just the people who are involved within the project, but actually the scientists who actually actively use this software. And we want to support the primarily scientific workflow that the scientists will have, but also there are a lot of industrial people who are connected to CCAM as well. So that's industrial community as well. And on all the supported architectures. By supported architectures, I mean, well, the way we think about it in EC is, well, the architectures that we support in EC, but we've made this commitment that we will look at whatever is supported in the Euro HPC space, right? Especially on those large-scale systems. And that was why we talk quite a bit about RISC-V and things like that, right? So our RISC-V support, because that's going to be interesting going forward in the Euro HPC space. We want to attract domain scientists, so there's a couple of ways that we want to do that. We want to make it easy for them to use new software. So that's where easy comes in. So we want to make it easy for them to try out new things and try out new software and get access to software. And then we want to showcase what we can do. So the scientific side, we want to do groundbreaking stuff, right? New scientific and industrial problems, and showcase how we do this co-design and how that can lead to good scientific outcomes. And the last thing is then on the training and knowledge development side. So we want to have a pretty extensive training program, both on the technical side about how to use things like EC, right? How do you use that in your workflows? But also like in domain specific, right? On specific codes, so like how to use particular codes that will be used within the project, and also in terms of workflows and how to leverage all the tools that we will provide for your scientific workflows. So that's for application developers and also for users as well. So those two different types of users that we will have. So just to give you kind of an overview of what the work packages look like there, I go into detail about the technical work packages, but just to put them up and show you what they are, there's 3 scientific work packages. The first one is about preparing the community codes for exascale readiness. What that really means for us is there's a couple of things in terms of libraries that we will develop. So one thing that we're interested in is load balancing libraries that are targeted towards the community. So a lot of communities use, for example, particle-based codes. So how do you balance particle-based codes? Because usually that means if you think about how a problem is split up over MPI in a grid, particles are free to move around that grid, so they change location. And then you get things like particles condensing together, so you get you can get severe load imbalance. How do you deal with that? So we have special libraries to solve that. And then another problem that usually takes a lot of computation is something like electrostatics. So then you want performance portable electrostatics library, something that will work on the different systems that will be available. And then there are other things that we are interested in pushing into the community a little bit, things that will make life easier for people to move to different systems and to scale on large scale systems. So tools like Focus, which gives you some kind of like accelerator independence or architecture independence within your code, allowing you to support new devices in a relatively straightforward way without having to rewrite a lot of code. So rather than using something like CUDA, which kind of restricts you in terms of where you can use it, you can use something like Focus, which will open up a whole array of possibilities for you in terms of where you can run your software. HPX, which is a runtime, so it kind of handles the execution of your code within the machine. And you can couple those together as well, which is also quite interesting. Something like, one of the software doesn't really have support for GPUs and things like that already, so they're looking at OpenACC. But probably we would even push them not to do that, but to actually do something else in the future. But the way it was written, that's what's in there right now. And so these are all community codes, right? So the idea that this will be pushed into community codes. And so we try and prepare people for what we believe will help them to perform well on exascale systems. And the second one is to develop implementation of interfaces. So MultiXscale is all about interfacing different things, right? Your different scales. So usually that means different software, even different mathematical approaches to how you approach these different length scales. And so there are 2 types of coupling. There's tight coupling, where you actually interface between different libraries and codes. And then there's loose coupling, which usually means workflows and things like that. So working with the data and transforming data and then using different length scale with that. The software that we will be looking at, there's a couple that were listed, but there probably will be more. LAMPS is one of those. MDFT, Espresso is another code that works with different length scales. While Beryl is a lot of lattice Boltzmann code, and then Urans, I can't remember what that's for, but that's related to the helicopter, so it's probably some fluids and things like that. Then the idea, one of the things that we want to do is look at modular architecture. So this is something that's promoted out of Jülich and probably has caught on, is that you have a system that has different capabilities on different partitions of the system, but you want to use them all at the same time, right? So you're looking at the entire modular spectrum, and then how can you concurrently use those and shift your work between those systems. The last one is the scientific targets that we have. So these actual workflows for sustainable industrial design. And those 3 things that I mentioned before, so helicopters and batteries, and then ultrasound as well. On the technical side, we have 2 technical work packages. The first one is developing a central platform for scientific software and emerging exascale technologies. you could translate that, and that basically means working towards EC, right? So we want to create a stable shared science software stack. Obviously, that's based on what we're doing right now in EC, and we want to make performance tuned, and we want to have it accessible for all the different platforms that will be out there. We want to expand the scope by supporting current and emerging system architectures. And obviously, what we'd be looking at certainly in the short term is what's supported in the Euro HPC space, or what will be supported in the near future. Just why we look at things like, well, we're looking at obviously accelerators. So, right, we will start to focus on in the future. We've already started looking at GPU support, so that would come with NVIDIA, but also we'll have to look at AMD as well. We don't have, for example, a Clang compiler toolchain right now in EC. We would need something like that. We also need interconnect support. So we have OpenMPI right now. That will probably get you a long way with on a lot of different sites, but it's not what everybody wants, right? Some people want vendor MPI implementations. There are tools out there to help you do that. So one that I've looked at recently, I mean, you have a couple of things you can work with. So one of the things is that you have ABI compatibility. So you should be able to swap in a new MPI implementation. I've tried it. In practice, it's possible, but not that easy. It's a bit difficult to get right. There is something else, something I've played around with quite a bit, called MPI Trampoline, and it's not the only one in that space, where you basically have a layer that you compile in, which is the MPI standard, and then on the back you can decide at runtime which MPI implementation you want to use. That works pretty well for C, but for Fortran, unfortunately, the reality is that the Fortran standard and the MPI standard conflict. So what people do in code is unfortunately break one or the other standard when they write their software, which means that for C stuff you can make it work and it works pretty well. For Fortran stuff you have problems. So I tried it with CP2K, and they break the MPI standard in multiple locations, and then you have this conflict about what do you do, right? Do you force the guy in MPI Trampoline to also break the standard that he's trying to maintain, just to make it work with Fortran codes, which is maybe what will have to happen in the end, but it comes with a performance cost, right? Unfortunately for him, and he obviously doesn't want this performance cost. So how do we deal with something like that? So this is the kind of things that we'll have to look at. We want to support the software developers to adopt these architectures. What does that mean for us? That means like looking at developer-oriented services, and we had this discussion about this continuous integration. We can create services to allow people to do that within GitHub, for example, or any CI that they might use. So we can, especially supported developers, we can allow them to trigger runs of builds of their software, or even execution of their software on the architectures that we have access to. And that doesn't mean that we will send them to it. We will run their code necessarily on a Euro HPC machine. It just means that we know what kind of hardware is out there. We can either get access to it through cloud environments, or we can emulate it or something like that. But we can at least give them access to some level of hardware so that they can run these things in CI. We want to improve the quality assurance of the shared software stack. So this comes back to the testing that we just had presented just now. And then we also want to provide services that facilitate the development of the RISC-V software ecosystem. So in the case of RISC-V, you have an issue in the sense that you don't really have a compiler, for example, for Fortran yet. So that's only coming, right? So, and this is in the Clang space, or like specifically what we're looking at is the Clang space. Then you're thinking about the Flang compiler, which is released now and is you can get it. So, but I still don't believe it's production quality yet. And also you have to get it work on RISC-V. So, and even RISC-V support within the Clang compiler itself there's something that's there. So I think it's functional, but it's not performance correct yet. So that's, and the performance of the Clang compiler on RISC-V is something that the Barcelona Supercomputer Center works on. But of course, when they're doing these things, they're not focused on something like Fortran code, right? So you have two things that are going on at once that you need to come together to make this ecosystem work for the wider audience, right? For the scientific audience. And one of the things we plan to do to help them is to make the compiler development easier for them. So we actually will release, as they tweak and tune the compiler, we can actually make releases of what they're doing, so they can test it on different systems, and other people can test it too, and they can also use it in CI as well, so that we can distribute these things and make that distribution like automatically updated, which should be very useful for them. The other one is supporting and maintaining the stack. So actually, so building it and supporting, but also the maintenance one is the one that's a big one in here. So we need it to be of production quality. It has to work on a lot of different systems and platforms. And that includes what we've discussed already, like the workstations, people's laptops, cloud environments, and the HPC infrastructure, all the way to the largest scale. We need to offer support. So we're going to have to support the community somehow for using this stack and any related services that we offer on top of that. And we need to make sure that they're going to have to be robust, they're going to have to be reliable, they're going to have to perform well. And that includes the different layers, right? So, I mean, the compatibility layer is one thing, but things like CPMFS, we're going to have to start worrying significantly about the performance of our distribution layer. And so we're going to have to actually monitor and test and maintain all of these components. And we need to facilitate and process the community contributions. So this comes back to things like ideas like the bot and everything, to be able to streamline these things and automate them as much as we possibly can, so that people can get their software into the stack in as efficient way as possible. Yeah, that's actually all I have. And we're back to the slide with the overview of everything. But maybe if anyone has any questions or anything like that about the project. Also online, feel free to ask.
Just wanted to congratulate one of you with this huge milestone. This is really important for the project, and I think it's going to force a bright future. So congrats.
Thanks a lot. I think that probably brings us back on time again, are we? I don't know what's the time now.
Maybe one last thing. So this is going to start early next year, essentially. So we're not quite sure yet when it's going to start. So figuring that out, essentially. So hopefully, if we do a meeting like this again next year, about a year from now, hopefully the impact of this is already very, very actually good. We were, I think in the milestones we mentioned in the project, we were fairly aggressive early on. So bringing easy to production is like one of the big things that has to happen pretty early in the project. And I got what we put down, but I think it also includes NVIDIA GPU. A lot of the things we've talked about today, the bot, NVIDIA GPUs, Intel and AMD support, that's like first half year or something into the project that basically has to be there and is stable.
I mean, certainly internally we'll probably be very aggressive when it comes to the first review of the project, right? That we make sure a lot of things are in place. So we'll be looking at targeting that first year. We already are, right? Looking at moving to a beta level.
We're actually preparing for it already.
Yeah, and we do have a table with things like technology readiness levels in the proposal, and we've been, I think, pretty aggressive there as well, right? In terms of what we target to do by the end of the project. Okay, no more questions then, we can move on to the next one.